In this video, I'm not going to be talking about functions. I am going to be talking about relations, okay? And it is going to seem like an elephant in the room, functions, because we are going to mention domain and range and other things that might remind you of things you discussed around functions, but we're going to cover something that's more general than functions. It's called relations. Functions are going to be a specific type of relation. And I gave you here a little chronology of how this particular book teaches that. So relations and functions follow. Other books do it similarly. I just wanted to show you that functions are not coming anytime soon, just the relations, okay? And here is the relationship between relations and functions. Functions is a smaller set, way smaller. This is not to scale. Okay, so this is the first example. Let R be a relation is older than, okay? And Margaret is an element and Maggie is an element. Margaret is 65 years old and Maggie is 25. Then Margaret and Maggie are going to be an element of relation R. A second way of writing that is Margaret is letter R related to Maggie. Or just write Margaret R Maggie, okay? And what that says is that Margaret is older than Maggie, because that's how I defined relation in this case. Okay, you have been using the second way of writing it your whole life, and you didn't even know that that was a relation. You would say one number is greater than the other number, and in that case, that's a relation, but you didn't think of it that way. So a notation for saying that a pair, Maggie and Margaret, don't belong to or are not a member of or element of relation R is to just cross out that symbol of is element of, or cross out letter R between. Because if you flipped it, the pair, Maggie and Margaret, that is no longer in the relation R. As I'm editing this, I wanted to clarify that elements of a relation are going to be ordered pairs, meaning that there will be a pair whose order, who comes first, will matter. In our example, Margaret has to come before Maggie. So it's Margaret and then Maggie, because Margaret is older than Maggie. If I define relation to be is younger than, then in that relation, Maggie should come first. Maggie, then Margaret. But you can see how the order of them will matter. And if you flip it, usually it will no longer be in the relation. Unless a relation is such that, for example, if I define relation to be is a sibling of, in that case, and in those rare cases, then you can flip it and it will still be in the relation. Because if Maggie's sibling of Margaret, Margaret has to be sibling of Maggie. And there are relations like that, whose inverses are equivalent to original relations, but those are rare. And you should never assume that that will be the case. So the definition of a relation is that it takes elements from A to B. So there is that direction there. Also, the relation has to be a subset of cross product between A and B. Let me explain. Cross products were covered before, but I will remind you what that is. So cross product is going to be taking every element from set A and connecting it, relating it to every element from set B. In this case, cross product will have 9 elements, okay? Margaret paired with Maggie, Gina, and Connie, Eugenia paired with all 3 of B, and Constance paired with all 3 from B. I picked out as my relation only the first one. That's one of the possible relations, because that's one of the subsets of A cross B, okay? There are tons of different ways. In particular, there's 2 raised to the 3 times 3, 2 raised to the 9th power, or 512 different relations or different subsets I can take from A cross B. So A cross B, the entire set, is one of the relations, one of the options, or empty set is one of the options. Elements of relation is going to be pairs, ordered pairs. Okay. So now, second example, using numbers. First and foremost, a relation has to be a subset of A cross B, and in this case, it is, and it has to take elements from A and connect it to B, okay? That's all from definition. In this case, Cartesian product or cross product of A and B will have 20 elements, but my particular relation has 4 elements, which are going to be ordered pairs. Okay, now I'm going to talk about, there's no new math here. I'm just going to show you different graphs, which will be useful to you to solve problems and to also deeply understand what's going on. So the first one is going to be this bipartite arrow diagram. So first, rectangle or box, or you can draw a rectangle. It's easier to draw on a piece of paper. We'll have every single element of A, and the second column or box will have every single element of B. And then arrows will be used to show direction from A to B. And then also to show who participated in relation R and who didn't. And here you clearly see that 3 did not participate from set A and 6 didn't participate from set B. Okay? Then the second graph is this T graph or table. And this just shows you who participated in the relation. The first graph, the bipartite graph, will never have a repeat because from the definition of a set, you don't have repeats. And every element is there once. But here, this is not listing out elements of A or B. This is listing out pairs that made it in the relation R. So you won't have a pair repeated. You will never have -1 and 5 and -1 and 5 twice. But you can have 2 from A and then 2 from A second time because they're related with different numbers from B. Okay? And the third way that you can represent it visually is putting set A elements on axis X and putting set B elements on axis Y, and then seeing where that relationship hit and putting those dots there. Okay, there's a fourth graph, but I will first explain what identity relation is. Identity relation is really useful. When I first learned it, I thought that its use would be limited and I didn't really pay attention, but it does come up later in your math classes. So what it is it's a particular relation that has its own name. Okay, it's identity relation and it is from A to A. So as your A, you're using set A, and as your B, you're using set A again. Okay, so you can draw it the same way, but both you're taking from A to A. That's by definition. The second requirement is that you need to use up the entire set A as your first coordinate and as well as your second coordinates, okay? So you can't have this scenario where you're not using one of the elements from the first column and the second column. You need to use all of them. And this is a necessary requirement, but not sufficient, because I can show you a relation from A to A that uses all the elements as its first entry in the pair and the second entry in the pair, and it's not an identity relation like this one. Because the third requirement of identity relation is that it connects elements to themselves. So 1 with 1, 2 with 2, A with A, and B with B in this case. If you wanted to draw it, you need to see horizontal lines and arrows going across, not diagonal. And in the definition, it says pair A and A. So that's the third. Now I'm going to talk about domain and range. And the definition of domain is going to matter. Put it on a separate paper because when you're solving the problems, every aspect of this definition will be tested. The domain of a relation is, for every x in A, there exists y in B, at least one, right? Such that x's are related to y. Because in the first case, 3 was not in a domain because 3 didn't even make it in the relation. So it can't be part of the domain because the domain demands that x, the last part of it, such that x is related to y. And there was no y where 3 was matched up with in B, right? Then range will be, another thing is that domain is nothing but a slot or a frame or a place where the domains go, okay? The first spot is for domain. Okay, now range, the definition is similar to domain. For every y in B, there exists x, at least one such x, that x and y are related. Again, in our example, 6 was not related to any of the elements of A, so that won't make it in range because we're talking about the range of a relation. It is the second spot in the pair, okay? So that's where the range is going to be found. Now, note that domain is going to be a subset of A. It could be the entire A. It always is for identity relation. It must be. Also, it could be other relations like that. And range is also a subset of B, and it could be the entire B for some relations and must be the case for identity relation. Now, the fourth graph that is used, and this one is particularly useful for understanding, but not that much useful for anything other than that. So its limitations are that digraphs are used from set A to A, and also it makes sense to use digraphs only for sets that have few elements, because in theory you can use it on larger sets with hundreds of elements, but then the arrows would be drawn on top of each other and you can't see anything, so it defeats the purpose of this, is to help you visually see what's going on. So here I have a relation, and the first entries or domains are going to be from A, and the second entries are going to be also from A, because that's what digraph is used for, from A to A. And I have 6, 12, and that's the bottom line. That's the first element in the relation, and that's the bottom line going from purple 6 to 12 for you. It's this way. Then we have 2 to 6. Then we have 2 to 12. That's the first arc, the bottom arc. Then 6 to 6, which is the loop from 6 to itself, okay? And then 12 to 2. Notice that there's nothing, no arrow around 5, because 5 didn't participate in a relation. Now the formal definition of the inverse of a relation, okay? The way that you form an inverse of a relation is super simple. You just take a relation and you swap spots of the first and the second element or domain and range. So if you had 1 and B as your first element, in the inverse of relation, you will have B1. And the second element, 1C, will become C1, 2C will become C2. And what you really did was that switch the spots of domain and range, and this right here says that domain of an inverse is going to be the range of original, and the range of the inverse is going to be the domain of the original. And there are proofs of this, but you can actually see this intuitively. This is what you would expect, because that's the algorithm through which you create the inverse. And from definition, if you gave me y and x belong to R inverse of relation, then I can automatically write down, and you do all the time in proofs, x and y must be in R from definition of inverse. Okay. Now, final topic we're going to talk about is going to be the composite, this idea of composite. And you've talked about composites in your high school with functions, and there's a lot of overlap of the words with relations and functions. I understand that. And with this composite, there's something weird that happens with composites, that you start reading like Hebrew or Arabic, like not from left to right. For you, it's this way, to right, but from right to left. And or from inside function is applied first. In this case, inside relation is going to be the R. That will be applied first, and second S, okay? So this will take 3 sets, A, B, and C, and relate A to C using or passing through B. B will be like a bridge. And any A that's not connected through B to elements of C will not make it in this composite relation of S composite R. For example, look at 3. It is connected to element from B, 3 and R, but then R does not take it to C. Okay, so then 3 is not connected to any element in C, so there should never be found 3 in your composite relation S composite R. Now, first one is 1 through P and X. So 1 and X I should find. Then 1 to Q and X. Okay, I can't have 1X twice, okay? You can't have repeats in a set. So 1 to P and Q, that didn't give me any unique. I just took 1 pair from that. Then 2 to Q and X, so that 2X, 2Y, those are unique. So I have 1X, 2X, 2Y, and 4Z. And that's all I'm going to have in S composite R. Because as you can see, then 5 wasn't mapped to anything and doesn't participate in this composite relation. Okay, now what's left to do is to solve tons of problems on these topics. Okay, thank you so much for watching. Hopefully this was helpful. Bye.